Quest. Okay, so we're going to talk about the energy stored in a magnetic field today. So I drew a very simple circuit here. I should probably add a resistor because every circuit has one. Wires themselves have resistance. Okay, so we have a very simple circuit. We have a power supply, an inductor, and a resistor. So say this is an actual solenoid. And if we wire these up, then there will be a current in this circuit, which will create a magnetic field in the solenoid. And say that we remove the battery, so there's no power. There would still be a current driven for a short time because of that inductor. So, like say we flip the switch to remove the battery from the circuit, the current can't drop instantly to zero. So there would, because of the inductance of the system, like in this case it would be a solenoid, and so there'd be an EMF that's powering that current as it's dying down. And again, it takes energy to drive a current, so where's that energy coming from? We interpret that as being stored in the magnetic field of the inductor. In this case, we're just going to deal with a solenoid because it's a nice example of an inductor, and it's something we can actually calculate. We did this before, but it's not too hard to do. Remember, for an inductor, the flux, the magnetic flux through the inductor is proportional to the current. So we can find the inductance of a solenoid, or any inductor, by looking at the total flux divided by the current. Now the flux through a solenoid, that'd be the magnetic field times the area. And, that would be, I want to be a little careful because we actually have a couple different, we use L for inductance. We normally use capital L for the length of a solenoid as well. Yeah, so I wrote the magnetic field of the solenoid here, using a lowercase l. So this is the length of a solenoid. Okay, but anyways, the flux would be this would be the magnetic field that's passing through every coil in the solenoid. So the flux would be the number of coils times the magnetic field times the area divided by I, the current. And so if we plug in the magnetic field, let's do this. NA times the magnetic field, and I'm going to remember to use a lowercase l here, so we don't mistake it with the henries. Now note that the current cancels out. Very important. The inductance of a solenoid has nothing to do with how much current is flowing through it. It's a property of the solenoid itself. So we can clean this up. I'll write the answer over here. U naught. And then we have N squared A over L. So again, that would also be for a solenoid. Okay, so we have the inductance of a solenoid. We did that before, but it doesn't hurt to do it again. Actually, I'm looking at my notes. I wrote it a little differently in my notes. Raise a lowercase n, and then add A times L. So remember, lowercase n is the turns density. So there are just different ways of writing the same thing. Okay, now let's go back to our circuit. We have a current passing through our circuit. So there's a current in the solenoid, which is creating a magnetic field. Now what happens if we increase the voltage by a little bit? Just a tiny amount. What's going to happen is the current is going to increase. But if we increase the current, that's going to produce a back EMF. And it's going to take energy to force this current through the inductor because of this back EMF. So again, if we just leave it alone, the flux is constant, but if we try to increase the current. So we could start out by imagining we just flip a switch. So initially there's no current at all, and then we're going to build up to a maximum current of I. But we're going to have to look at it in kind of pieces. We're going to start out, say we're at just some arbitrary current, and we want to increase it by a little bit. We're going to have to do work in order to do that, because we have to overcome this back EMF that comes from Faraday's law. And so remember, to force a charge through a potential difference, or delta U is Q delta V, let's say the work that we have to do. So we're just going to increase the current by a little amount. We'll call that delta I. So our current is going to go from I to I plus delta I, where delta I is just a small amount of current. So what we're going to do, we'll call delta W the amount of work required. And that'd just be the charge times this EMF given by Faraday's law. So basically just this equation here. Okay, so we can combine these two equations. I know this is on the equation sheet, but the EMF depends, just by plugging the flux in here, the EMF depends on how rapidly you're trying to change the current. So delta I over delta T, that's how quickly you're changing the current. If you try to change it very quickly, there's going to be a strong back EMF. So let's plug that in here. So we have Q times L delta I over delta T. And I actually want to modify this. We're just changing the current by a little amount. We're looking at a small change here. Let's just call this delta Q. So delta Q is the amount of current we push through the inductor in a time delta T. And I want to rewrite this a little bit. Let's say delta Q over delta T times L delta I. And delta Q over delta T is just the current. So we get this result that the amount of work it takes to increase the current by an amount delta I, that's proportional to how much current we initially have. So delta W, let's write down this result. I'll move things around if needed. So the amount of work for a small increase in current is Li delta I. Now ultimately, let's say, what if we start with 0 and increase it to some maximum current? Now this is a difficult thing to calculate because the current doesn't have a fixed value. It's starting at 0, ending up. So let's say we plot the current as a function on the horizontal axis, and on the vertical axis we plot the inductance times the current. So what we get here is a line going through the origin with a slope L. Okay, now I'm going to call this our maximum current. So we're going to start at 0, go up to some maximum value. And let's just look at a small change in current. So we start out with a current I. We end up with a current I plus delta I. So the amount of work is given by this equation, here. So if this is I, then this level here is Li. And the thickness of this rectangle is delta I. We're going from I to I plus delta I. So that we have a rectangle here with a thickness delta I and a height Li. And so basically, if we ignore this little triangle here, the amount of work is just the area underneath this curve from here to here. So if we just find the area underneath here, this is approximately equal to the area. Let's say approximately equal to. However, we can improve this by making delta I smaller. If we make delta I smaller, this triangle is going to become fairly insignificant. We can always make delta I to be small enough so that this area is much larger. The area of the rectangle is so large compared to the area of that triangle that we can disregard it. And so we can interpret the work required to build up a current in an inductor as the area underneath this curve. So let's go from 0 up to the peak current. So the total work, we just have the area of this whole triangle, which is 1/2 times the base times the height, which would be LIM, or 1/2 LIM squared. So let's do that. 1/2 L. So if we start with 0 current, build up to some maximum current, and again, the maximum current in this case would just be V over R. The inductance doesn't affect the total, the eventual current that we'll get. It only affects how long it takes to get there. But yeah, so that's how much energy. Again, this is work we'd have to do to increase that current from 0 up to its peak value, because the inductance of the system is opposing that. So that makes it difficult to build it up. We have to put energy into it. And now once we get peak current, nothing is changing anymore. But again, there's energy stored in the system. Like if we had this flipped up to a switch, where we could flip a switch and remove the battery from the equation, the battery is not powering a current anymore, so it wants to drop to 0, but the inductor is going to continue powering that current as it's dying down. So it's not going to drop immediately to 0. So again, it's going to take energy to do that. And so we say the energy is stored in the magnetic field of the solenoid. And now we want to get an idea of how much energy is stored here. So we've got a solenoid which is storing all the energy in the circuit. Like once we reach this peak value, there's a certain amount, like all the work we put into it is stored in the solenoid. So let's look at, start with the total energy which is stored in the magnetic field. So we have 1/2 Li squared. Now for a solenoid, we know the inductance is mu naught N squared A over L times the current squared. And we've got the solenoid. I'm not going to draw all the loops on it, but it has a length L and a cross-section area A. So actually what I'm going to do, or the turns density is big N over L. So the number of turns is the length times the turns density. Let's throw that in there. So we have mu naught, N squared would be little n squared, times, well, it would be consistent, use a lowercase l. I'm going to do this. Okay, so Your big N squared is little n squared times L squared, but we're dividing by L, so there's just one left. And that's what we have so far. And so we don't need parentheses here. Let's say V is the volume of the solenoid, which would just be the length times the cross-section area. And so V is the volume. Don't mistake that for voltage. We'll write out VOL just to be safe. And let's divide the energy over the volume. So we have mu naught n squared I squared. This is the energy density. So remember we did this with capacitors and electric fields. We looked at the electric field only exists between the plates of the capacitor. And so we had like a volume, we found the energy density for a capacitor. Now we're doing the same thing with a solenoid. But I want to get this in terms of magnetic field. So here, and we erase this. So again, the magnetic field in a solenoid is mu naught. I'm going to convert this to big N is little n times L times I divided by little l. So the magnetic field is just the, that constant mu naught times the turns density times the current. And so we kind of have that here. Let's write it this way. So what we did is, mu naught squared divided by mu naught is mu naught, and then the rest of it's there. So what we have is the energy density. We use a lowercase u for that. And that's the end result that we wanted. So the turns density is 1 over mu naught times b squared. All this is just b, the magnetic field in the solenoid. And so we see that the energy density is proportional to the magnetic field squared. Just like with capacitors, we found that the energy density was epsilon naught E squared. So again, it's kind of the same thing. The energy stored in an electric and magnetic field, it's proportional to the strength of the fields squared, regardless of which type. Now they have different constants, but yes, now we've seen how much energy is stored in both electric and magnetic fields. And the main reason we're doing this is because soon we're going to talk about light, which is a form of electromagnetic radiation, and light carries energy. So, this energy density of light, that's very important. And so we're going to need both of these results for what's coming up. So that was the main reason to motivate this. But yeah, the energy stored in the magnetic field, the energy density proportional to the magnetic field squared. So that'll be it for this one.